Now in this video we discuss the convergence of another important sequence, which is r to the power n, and the convergence of this sequence will depend on the value of r. Okay, so we'll do it step by step. Now simply what we need to find is whether this sequence converge for these given values of r. Okay, so to start with, let's consider the case where r is greater than 1. Okay, so when r is greater than 1, we can see now we are dealing with this sequence. Okay, and remember the first theorem we did was we can consider the corresponding function with x goes to infinity, and this limit will be the same as the sequence limit, right? So here what we are going to do is for this case we consider the corresponding function, which is rx, and then we consider the limit of x goes to infinity. And we know that if r is greater than 1, now this is a known fact. Okay, so if r is greater than 1, the graph of these types of functions, which are called exponential functions, now here this r need not to be e all the time, right? You might be familiar with the graph of this one, but this base need not to be e all the time. It can be any number greater than 1, but still the shape of the curve will be exactly the same shape, right? But the values will be different, but still it will have a same shape and with the same intersection. So you can see now when r is greater than 1, the function will go to infinity when x takes very large values, right? So in other words, the limit of this one will be equal to infinity. So from that theorem we can say the limit of our function, limit of our sequence will also be equal to infinity when r is greater than 1. Okay, right. And then how about the other case? Let's take the case where r is less than 1. When r is less than 1, then once again we can consider the function r to the power x, right? So now here you can see if r is less than 1, let's take a number like 0.5. You can see when you are taking higher powers of this same number, which is less than 1, that number will be reduced. Okay, so like say for example 0.5 to the power 1 is 0.5, and this one to the power 2 is 0.25, which is less than 0.5, right? So this is kind of a property of numbers which are greater than 0 and less than 1, right? Now here we are taking the values greater than 0. Okay, so this is kind of a property of these types of numbers. When the power is large, the total value will be reduced, right? So in other words, this function will go to 0, right? Then once again from that above theorem, see, we know the value of the function, so we know the value of the sequence. So the value of the sequence will also be equal to 0 when r is less than 1 and greater than 0. And how about the case where r is equal to 1? So when r is equal to 1, what we have is if we just consider the sequence as this one, this will be r to the power 1, r to the power 2, r to the power 3, r to the power 4, likewise. So as r is equal to 1, what we have is 1, 1, 1, 1, and so on. So we will end up with the constant sequence 1. Therefore, this constant sequence, limit of a constant sequence is the same number, because this is the only number that the sequence can approach, right? So the limit will also be equal to 1. And how about the case where r is equal to 0? Then the sequence will be equal to the constant sequence with zeros as the position values, right? So this is the r1 position, this is the term related with r2, and this is r3, r4, and likewise. And since r is equal to 0, all these terms will be 0, and hence the limit of this sequence will, when n goes to infinity, will be equal to 0. Okay, so now so far we have discussed several cases for the same problem. When r is greater than 0 and less than 1, and when r is greater than 1, and when r is equal to 1, and the case where r is equal to 0, right? So we have dealt with, like if we consider the number line, we have separated the values of r into several sections. The values of r which are greater than 1, and at 1, from 0 to 1, and at 0. Now how about the other side? So for that one, once again we will separate the number line into two sections. Now for the values in between -1 and 0, now we have already dealt with 0. How about this one? What if r is equal to -1? Then the sequence will be -1 to the power n. And in a separate video I said that this sequence does not converge. That means the sequence will diverge, right? So the sequence will diverge when r is equal to -1. And how about the terms in between? That means r less than 0 and greater than 1. So for that, what we can do is, in order to determine the convergence of this sequence when r is within this range, what we can do is we can use the this theorem, which is this one. The modulus, if it is equal to 0, then the sequence without the modulus will also be equal to 0. So we can use that result to determine the convergence when r is in between 0 and -1. So here what we can have is like, now we have to find the convergence of this one. So instead what we do is we consider the convergence of the modulus, right? So when it comes to the modulus, we just have to take the modulus of the whole thing, and that is equal to the modulus of r to the power n. That's a property of the modulus, right? So that means instead of taking the limit of this one, we just take the limit of this one, right? So that means the limit of this one. And now since we are considering the modulus of r, that means we have a positive number, but it should be less than 1. Now in this case, the r is greater than -1 and less than 0. So if we take the modulus of r, now originally r was between 0 and -1. But if we take the modulus, everything comes to the positive side. So R will be between 0 and 1, right? And we already showed that if R is in between 0 and 1, the sequence will converge to 0, right? So in other words, when R is less than 0 and greater than -1, the modulus of Rn that is equal to the limit of modulus of R to the power n, and this is equal to 0 because this is a term in between 0 and +1. Therefore, we have shown that the modulus of the sequence is equal to 0, and from the theorem we can say that the original sequence, therefore the limit of the original sequence will also be equal to 0. Now we are in this stage, right? This component. Now we have to deal with the other part as well. What happens if R is strictly less than 1, strictly less than -1? What about this case? Then, like for example, let's take R is equal to -5. Then what will happen to this number? That is this one. So let's obtain some random values. When n is equal to 1, then R to the power 1 will be -5. When n is equal to 2, R to the power 2 will be -5 squared, which is a positive number, right? And when n is equal to 3, R3, and then it will be a negative number, negative, but the number is very large, right? So what will happen is, if we plot the graph, what we will get is, for each and every natural number, the values of the sequence Rn when R is less than -1 will be like this, right? It will start from a certain point and it will go up like this, and it will go down like this. So it will oscillate in a very wild way, right? So it's like, now so far we have discussed several types of oscillations, right? The first thing is the distance between these 2 points was the same, and the example was -1 to the power n. So all the time, no matter what n we choose, we will get either -1 or +1. And the other case was -1 over n, and in this case the sequence oscillates, but they were getting closer to each other, and eventually it will reach 0. So in this case it was a converging sequence, and in this case it was a divergent sequence. And this case, this is also an oscillation, but see, the distance increases with the value of n, right? So definitely this is going to be a diverging sequence, because there is no way for this sequence to converge to a certain point, to get closer to a certain point. Like even this, it was not possible for the sequence to get closer to a certain point. So this, like this third condition will definitely say that, like you can observe that this has no way for the sequence to get closer to a certain value. In other words, the sequence will diverge when R is less than -1. So what we have done so far is a very important result. Okay, now this is not a theorem kind of a thing, but this result will be important and also will be used in the future, right? And the result is, this sequence is convergent only when R is in between between -1 and 1, right? So here -1 is excluded and +1 is included. So if this is the number line, for values between 1 and -1. See, for the -1 you have an open bracket, and for the +1 you have a closed bracket. Okay, so for all these values the sequence will converge, and for the remaining values it will diverge.